All right, hello everyone. Our project is the Exoskeleton Wrist Assist. My name is Emily Nunez.
My name is Kristen Bermudez.
My name is Melissa Villegas.
And these are our objectives. So the first one is to create an exoskeleton wrist assist to provide aid for people who have lost mobility in their wrist and require physiotherapy. Our main focus is to overall better increase the performance for a broader range of movement and the types of movement, as well as remaining flexible, lightweight, cost-effective, and ergonomic. The medical purposes are to help stroke patients, aid in physical therapy, and aid in wrist rehabilitation. And this is our approach. So we use the engineering design process as pictured in the left. And we did this by first, we did our design that connects the hand to the forearm for an easier and cleaner wrist motion, as well as making it user-friendly by having a simple mechanical design. And we utilize sensors in order to be able to measure the amount of movement being made. And we remained low cost, safe, and a simple design. So our first task is to measure the movement based on regular range versus exoskeleton range. We are going to measure flexion, extension, ulnar deviation, and radial deviation. And our second task is to measure speed. We will set a timer for 20 seconds and compare the number of repetitions that an impaired hand can do by itself and with the exoskeleton on.
So we have the preliminary model changes we had to make. So in our first exoskeleton, we had a motor on top being, and I'm sorry, we had the exoskeleton with the motor being attached on top, which made it super heavy, and it was also an entire glove. So we used this idea and changed it into having a hand brace and having a forearm brace in two pieces. And then we further developed this idea by having an entire mechanical aspect on the arm and having an electrical box on the side connected through wires. So the main reason why we did this is because everyone has a different sized hand. So finding a universal fit is really difficult. So that was our main reasoning for breaking up into parts. So next we go into cost analysis, which there are two categories, prototype and actual. So in both of these categories, we have the material, what it's made out of, and the price tag along with it. So for the glove in our prototype is made out of cotton. Pulleys were plastic. The string was fluorocarbon or a type of fishing wire. The wristband was made out of mixed materials, and the wrist brace, which we didn't use but was still involved in our price tag, totaled out to $60. If we were to build this in actual, the glove would be 3D printed out of PLA filament. The string would be twine. We have two flex sensors, 4 servo motors, a microcontroller, which is an Arduino Uno, and other miscellaneous items such as batteries, wires, and resistors. So our actual would total out to about $108. So if we estimated about $100 for prototype and $300 for actual, we totaled out to $400. But realistically, we only spent $60 building the prototype. And if we were to build it actual, it would be about $110. So only using $168 out of $400, we use less than 50% of our estimated budget.
In our prototype, here are a few pictures of how it should look like and how it's going to look like. We have the top view, which is with the 2 pulleys, and then the right view along same as with left view and bottom view. All views have at least for the bottom, there's always going to be 2 pulleys, and then the top is going to contain also 2 pulleys, and then eventually each pulley will have a motor. So depending where your hand is moving, you should, the pulley will move with the motor as well, but then the other motors that are not moving are just going to stay. They're going to be shut off. So that's how they're going to measure the bending when there's mobility occurring. There's also a video, and that I'll just show you real quick. That video just basically shows how the movement is going to occur, how pulley, it doesn't show which pulley is moving, but if you move to the right, only the left pulleys, top and bottom, are going to end up moving by itself. Next.
So we have two proposed tests that we couldn't perform due to the virtual format. The first one is movement, and we would test this by having a stroke patient move their impaired hand and doing the same thing with the exoskeleton on. This test would be performed by having the patient move in the following four movements: flexion, extension, radial deviation, and ulnar deviation. The range of the movement will be measured by using a goniometer, which will allow us to accurately measure the angle that the patient has moved. This is often used in physical therapy to measure the range of movement because it has one stationary side and one side that the user can move. There is also an app that would allow us to measure the range by opening the app and placing our phone in the correct position and then moving the body part that we want to get the angle for. And each test will be done 3 times, and the average will be taken and displayed in the table below. And then moving on to our second proposed test, which is speed. A timer will be set for 20 seconds, and the patient will move their impaired wrist without the exoskeleton and then again with it on. And the patient would do the same 4 motions, 20 seconds each: flexion, extension, radial deviation, and ulnar deviation. And we will count how many repetitions the patient can do in the allotted time. And each movement will be done 3 times with the average displayed in the table.
So we have the computer architect design in the mechanical aspect. So for CAD, we use the program SolidWorks, and all parts are custom made and not downloaded except for the hand. So for the mechanical components, we have in figure A, the forearm band, in figure B, the pulley, the hand band in figure E, which will be shown later on, as well as the flex sensors in figure F, the hand in figure L, and the twine in figure O. So as mentioned in figure A and B, these parts were used to show in figure C, where we have a top view of the assembly of these components. And in figure D, we have the isometric view of figure C. So this is to show you guys that there's 2 pulleys on the top and 2 pulleys on the bottom for a total of 4. So on a continuation of that, the small handband will have extrusions in later versions that will show in the slides, but as of now, it just has a smooth coverage to show you guys how well it fits with the other pieces. So even though a sensor is considered an electrical component, right now it's referred to as a mechanical component because we're attaching it to the arm portion instead of having it tucked away in the electrical box. So the flex sensor on the left side of the brace is used to capture ulnar and radial deviation, and the flex sensor on the bottom is going to be used to capture wrist extension and flexion. So as figure E and F show, these are the individual parts, and figure G shows the assembly of all the previous parts mentioned. For the electrical components, we have the user remote in figure I, the electrical box in figure H, the microcontroller, which we're using in Arduino Uno in figure J, the servo motors later on in figure P, and wires in figure Q. So the electrical box contains most of the miscellaneous parts, such as jumper wires, batteries, resistors, and even a small breadboard. Then the final assembly includes a total of 20 parts. So as you can see in these photos, in figure K, we have the assembly of all these individual pieces that make up the electrical component. Next comes the hand fitting. So we have in figure L the actual hand that was downloaded. So this was from a place called Thingiverse, and it's an open source. And since this shows that even though it was a random hand off the internet, it shows that our hand brace is a universal fit, so one size fits all. So as is shown in figure M, it fits pretty well within our brace. And figure N just shows a top view, so you guys can see the electrical box too. Next comes the connectors. So there's twine in brown in figure O, and there's 4 pieces of twine in total, 2 on top, 2 on the bottom. Electrical wiring in gray in figure Q, and servo motors in red in figure P that are attached to each pulley for a total of 4. So there's 2 on the top and 2 on the bottom. Finally, we have the all assembled figure. As shown in figure R, we see the top view of the finalized assembly. That's all the components we've talked about so far put together all in one photo. And figure S is just the side view of that, so you guys can see the top and bottom pieces as well. So next we have the electrical block diagram. So this shows all the possible options to take with the exoskeleton brace. You can use a computer, user remote, or both to start this process. The microcontroller is the most used block as it has 3 pathways leading to it because it's the most compatible with other devices, which means the computer, the user remote, and the flex sensors. So a popular pathway is to use the computer to go back and forth towards the microcontroller following this black loop of arrows. The next popular pathway is using this, again, black loop and have it repeat on itself through the pink arrow and continue that way, or use the black arrow loop and have it go around towards the green and back again. Or we have the going through the brown arrow way through the black loop into the pink and repeating so on.
So in our schematic, it contains various components. We have 4 servo motors, 1 for each pulley. So it's going to be 2 on the top of the brace and 2 at the bottom. And then we also have 2 flex sensors. One of the flex sensors is going to measure when there's mobility going up and down. And then the other flex sensor is going to measure the bending of the mobility, during the mobility, moving left to right. The schematic also contains four push buttons and a switch. That is going to be the remote that the person using with their healthy hand is going to be able to control the brace. So they're going to be able to move up or down or left to right. And the flex sensor already has a high resistance without even bending it. So it already has a high resistance without the possibility of moving it. But once you're moving it, the bending will increase, which will create a higher resistance. And then we also use, and then basically this is what our schematic will contain. Everything's connected to the Arduino because mostly all the components are 5 voltage used, which is pretty good for our circuit.
And so these are our future improvements, would be to add in the only form of movement that we're missing, which is displayed on the right-hand side, is pronotation and supintation. And then to get these movements, we would make the necessary changes to the mechanical design by adding extra servo motors, pulleys, and twine if needed. And also making changes to the electrical design to add in any extra flex sensors, resistors, or wires needed, and as well as adding more complex code into the microcontroller to allow the user to have the option to do preset routines. And this can include either preset routines of the flexion and extension repetitions or the ulnar and radial deviation repetitions. And then this slide displays our sources used to gather the information found in this PowerPoint. And thank you for listening. That is the end of our senior project.